is obviously 9, 6. Sketch the graph of the polar equation. This one says r equals 6 sine of 3 theta. So the first thing we want to do is classify it. What kind of equation is this? This is a rose. Sorry. You're welcome. Okay, and I know that because there is a number in between the trig function and the theta, but the r is not squared. Okay, if it was squared, it'd be a lemniscate, right? So when it's a rose, we have to identify how many petals it has. How many petals does this have? 3 petals. If it's odd, we keep it. If it's even, we double it. Then we have to identify how long each petal is. What's the length of the petal?
6.
Which is the number at the front, okay? And then we'd identify if there's polar axis symmetry or pi over 2. Which one? Pi over 2. So I know that everything that happens on the right-hand side is going to happen on the left, which means my 3 petals are either going to be like 2 in the top, 1 in the bottom, or 1 in the top, 2 in the bottom. So the easiest way to figure out where that petal is by setting this equal to the petal length. So I'm going to change r so that it's 6. 6 equals 6 sine of 3 theta. Divide both sides by 6. I get 1 equals sine of 3 theta. Where is sine 1? It happens at pi over 2. And then divide both sides by 3, and I get 1/3. So is this the same example I gave you yesterday? Pi over 6, 3, would be where one of my petals is. So if I go pi over 6 and I go to 3, 1, 2, 3, I know I have a petal there. Because there's symmetry over the y-axis or the pi over 2 axis, that means that the other petal happens at 5 pi over 6. And then there should be one underneath at pi over 2. Now the way I confirm those two is by plugging in those points. So I would plug in 5 pi over 6, 6 sine 3, 5 pi over 6. This gives me 5 pi over 2. 5 pi over 2 is all the way around and back up to the top. So sine there's 1, and that's 6, which is consistent with what we found. And then the one on the bottom, 6 sine 3 times pi over 3 pi over 2. And I get 6 sine 9 pi over 2. That's 4 1/2. Brings me around twice, back up to the top. So sine there is 1 again. And I get the other coordinate point.
Wait, why is it pi over 2 symmetry again?
Because it has sine in it. Sine and the r is not squared.
Okay.
So if the r is squared, the sine rule goes out the window. The shortcut, right? Then we have to test by actually plugging in points. Or just remember your lemniscates are either just to the pole or pole and polar axis if it's cosine.
Okay.
So the way your test, I started building your test yesterday. The way your test will work is I would love to give you all 4 graphs. You'll never finish. So you're going to get 2 graphs. You're going to get a limison for sure. Like depending on your version, you're going to get either a cardioid, you're going to get a convex, you're going to get one of those 4. And then you're either going to get, wait, that's a lie. I think I gave you 3. And then you're going to get a combination of like the rose, the lemniscate, and the circle. Okay? So you will get an easy-ish one mixed in with, I think, the ones that require the most work, which is the limison. Yeah. So just be prepared for all 4. Okay? The second one is your limison. So I'd have to distribute this 3 in here. I'd get 3 minus 3 cosine theta.
I'm confused. How do you know that that's a limison?
It's the only one that has a plus or minus on it.
Okay.
That's the easiest way to see it.
Okay.
And then, first of all, the r squared's lemniscate, right? The last one we just did has a number in between, but it's not r squared, because the r squared also has a number in between. But the number in between the trig function and the theta, that's your rose if it's not r squared. So r squared to me is the easiest to identify. R squared, lemniscate. If it's not an r squared, is there a number in between? That's a rose. If there's not a number in between, are you adding something? That's a limison. And then if it's just one thing, if it's a number, sine or cosine theta, that's a circle.
For the r squared, there's no shortcut. Like you have to plug it in, right?
No, the r squared, we found the petal, and then we just duplicated it on the other side.
Like you have to plug it all in.
Yeah. These are the ones that require the most work, the limisons. Yeah.
Because there's no, like, the sign.
There's no petal. Right, yeah. Well, no, we know the symmetry here, right? This would be symmetric.
Oh, okay.
right, to the polar axis because it has the cosine in it. Yeah.
But if it was r squared, then it's like you have to.
R squared with cosine is symmetric to the polar axis and the pole.
Oh,
R squared
okay.
with sine is just the pole.
It's just the pole.
Yep. So now I look at my A and B. Remember, you don't use the sign. So A is 3 and B is 3. What happens when A over B is 1? It's classified as a what? A cardioid or a heart-shaped, right? I don't even know if I spelled that right, but you know what it's supposed to be.
If it's less than 1, it's the loop.
Less than 1 has inner loop. Cardioid is the heart. In between 1 and 2 is your like the one that looks like a kidney bean. And then the last one is your convex one, which is if it's bigger than 2. Yep, it's flat on the side. All right, so now I got to plug in some points. I know that it's symmetric to the polar axis, so I'm only going to plug in top to the first quadrant and the second quadrant. We're going to cheat a little bit this time and do a little bit less points because you're going to see what's going to happen with the cardioid. The loop, I would say you need a little bit more. But the cardioid, I know it's going to come in and then come back out again. So I'm actually going to plot 0, pi over 4, pi over 2, 3 pi over 4, and pi, and see if we can get our shape.
That should be good enough.
Is it okay if I did the 5?
Absolutely. So I'm going to plug in 3 minus 3 cosine 0. The cosine at 0 is 1. So 3 minus 3 is 0. So it's 0, 0, which means my coordinate point starts here. Then 3 minus 3 cosine pi over 4. Cosine at pi over 4 is root 2 over 2. 3 minus, and this root 2 we're going to approximate to be a 1.4. That would be 2.83, times 1.4 over 2. 4.2 over 2, so 2.1.
So
1.1, comma, pi over 4.
Okay.
So I know I'm going just a little bit past 1 on that pi over 4 line. Then I'm going to go pi over 2. 3 minus 3 cosine pi over 2. 3 minus 3 cosine there is 0. 3 minus 0 is 3. So I get 3 pi over 2. Now I'm 1, 2, 3 all the way up here. Then I go 3 pi over 4. 3 minus 3 cosine 3 pi over 4. 3 minus 3 times negative root 2 over 2. This is 3 plus, we just estimated this to be 2.1, right? 2.1, so 5.1. So pop 5.1 and 3 pi over 4. And then the last one we're going to plot for now, 3 minus 3 cosine pi. Cosine of pi is negative 1. 3 plus 3 is 6. 6 pi. That's not 6, that's 5. 6 pi. Then all the points I have at the top, I'm going to duplicate down on the bottom because this is symmetric to the x-axis or the polar axis. So that 3 pi over 4, 5.1 is going to become 5 pi over 4, 5.1. The pi over 2, 2 is going to become, or sorry, pi over 2, 3 is going to become 3 pi over 2, 3. And then the pi over 4, 1.4 is going to go 7 pi over 4, or 1.1, not 1.4. And then I connect them. And it should have a sharp little point because it's a cardioid. So that's one of the ways you know. One, if it was a dimpled limicon, it should have a smoother transition there. It shouldn't be so sharp. But you know to make it smooth or sharp based on classifying it as a cardioid or a dimpled or the one that looks like a kidney bean. If those over 4s were not enough information, then obviously I'd have to do the over 6 and the over 3. I would say for sure if it's an inner loop, you're going to need the 6 and the 3.
Because you need to find where the loop is.
You need to find more points. Yeah, otherwise you're not going to get the loop. But this one, I would say if it's almost anything else, you could just go to the 4s. Questions? Okay, so this was the first question from the homework, which is good because we didn't do this one right in the warm-up, okay? This is number 7 from the homework. This is a what?
It's
A lemniscate. And I know that because the r is squared. It's the only one that has an r squared.
Okay.
So this is your little infinity. So it's like a rose with 2 petals, really. Okay, so I know it's a lemniscate. It's got a cosine in it, so it's going to be symmetric to the pole and the polar axis. Which means it's either top and bottom, like vertically, or it's horizontal. I just got to figure out which one. I know that the length of the loop, this a squared equals 4, a is 2, and that's the length of the loop. So loop length, I guess. I don't think it's called a petal. I don't even know. That's 2.
I got confused because like in the picture that was what's
So it's not a rose. Yeah, but you won't get multiple choice, so it's good. I'll work it out anyways because you're not going to get multiple choice graphs.
Okay.
Yeah. So I know the loop length is 2, so if I wanted to find where that loop happens, I just plug in 2 into the r. So 2 squared equals 4 cosine 5 theta. This would be 4. This is always going to happen if you do it correctly. You'll always divide, and it will always give you 1 equals whatever that cosine is. That step will always happen if you do it correctly. So now I'm trying to figure out where cosine is 1 and cosine is 1 at 0. 0 equals 5 pi, divide by 5, and I get theta equals 0. So now I know that the one loop happens at 0, and the length is 2. So I know this is happening, and then I assume because it's got polar axis and pole symmetry that the other one is happening over here. I missed it, but you get it. And to get 100% clarity on that, I would plug in pi. So r squared equals 4 cosine 5 pi. 5 pi is an odd whole number, which means it would be on the left of my unit circle. The cosine there is -1. Ooh. R squared equals 4 times -1. R squared would equal -4. Did I do that right? Yeah. And then it would be negative, so you're not going to get that point there. If you were to plug in 0, you would get a plus and minus square root 2, which is where that second point comes from. So if I were to plug in 0, I'd get r equals plus and minus the square root of 4, and r equals plus and minus 2. And that's where both the +2 and the -2 come from. So we couldn't get it with the pi, but we can get it with the 0. So the plus and minus is where that's going to happen. So the same thing could happen with your like pi over 2 and 3 pi over 2. One might be nothing, but the other one might get you the plus or minus. So, yeah, that's all you need for those. You just need to find the loops. What do you mean?
How did it get one with so many?
It's just trying to throw you off. Because it knows you're going to look and see it's a 5 theta. Oh, that's a rose. Let me give it 5 petals. Uh-huh. Yeah. And it's just going to throw you off. Yeah. Which you won't get multiple choice anyway, so.
So which one's the graph for it?
The graph, I don't know where it is. I didn't take a picture of that part. So again, I'm teaching you how to use your graphing utility just to help you check your answers on homework and stuff like that. You will not have your graphing utility on your test. Don't get too comfortable with it. Don't plan on always having it. You won't have it. And you're definitely going to have to show all that work. So if it's a rose, you're going to have to show the length of the rose, like you're going to show the number of petals, the length of the petals, and then figure, at least show the work to get one of the petals and then the symmetry. All of them will have symmetry that you'll have to check for, that kind of stuff. But something like this, we didn't do ones where there was the 3 at the front, so you don't have to stress about it. We did the rose ones where there was just, not the 3 at the front, but the -3 inside. You don't have to worry about that. It would just be the same. Everybody good? Questions? Okay, like I said, we're literally just going to get a head start into 10-1. So 10-1 is called the three-dimensional coordinate system. We are literally going to learn how to plot a point on a 3D coordinate system, which is really super fun when you're teaching this on a 2D device. It gets pretty weird, okay? And then we're going to learn how to find the midpoint, the distance, and the equation of a sphere based on these things. So a three-dimensional coordinate system, okay, has space. It has an x, a y, and a z. The x usually runs, not always, but usually runs just like your normal x-axis, left and right, horizontally. This could typically be your x-axis. Your y-axis is typically your up-down, right, your north-south line. And then your z is now going to come forward and back. So this would be, again, in a three-dimensional space. This could totally rotate around, however. So you have to pay attention to where the letters are. If x is rotated to the front, now your z is going to be on the side, the y might be up. Or they could rotate it completely around. So just pay attention to the label of the points. Yep. Okay, this is where you start to get into what's called solid analytical geometry, when you start to add in that third dimension. You can construct a 3D coordinate system by passing a z-axis perpendicular to the x and y, which is what I just showed you. The figure below shows the positive portion of each coordinate axis. So if I was just to look, notice that the x is here, the y is here, and the z is here. If I was to just use the front right corner of that, if I could picture it like a cube, okay? If you were to use the front right corner of it, then it's going to be the positive on the x, the positive on the y, and the positive on the z. And it forms three planes, okay? Remember, two lines can form that plane. So if I were to look at this, let me match the colors. This plane here on the bottom, the green one, that's formed by the x and the y. If I was to look at the one here on the left, that's formed by the x and the z. And then the one in the back, that's formed by the y and the z. So they're named by the two lines that lay in them, or the two axes that lay in them. If you could picture it to be like a beginner Rubik's Cube, it could be like a cube that has the 8 different boxes, and those boxes are called octants, because octa, 8, okay? So the first octant is the one in which all three coordinates are positive, which is what we just looked at. In a 3D system, a point P in space is determined by the ordered triple x, y, z, where z, y, and that should be x, y, and z, would look like this. So if notice that my x is now forward and back this time. Remember I said it could rotate. You move in the direction of the x to get the x coordinate. So in this case, we move in this direction. You move in the direction of the y, which is over here this time, to get the y coordinate. And then you move in the direction of z, which in this case is up, to get the z coordinate. So you're going to pay attention to where they are. Usually the x and y runs left to right, so a little different than we're looking at right now. And we would move right that many spaces, and then the y and the z is forward and back. We'd move that many spaces, and then the z is up and down, and you move that many spaces. All right, every year I forget to cover this up. Is yours covered? Is yours whited out? Yeah, every year. You think I'd remember. This says determine which is the point 2, -3, 3 in the coordinate plane below. Okay? So notice the different axes. Remember I said you got to pay attention to where the letters are. The x-axis is here, which is actually forward and back. So if I wanted to find 2, -3, 3, I got to find the point that moved forward 2. The y is right left this time, so it's got to come right 2, diagonal right. And then the 3 has got to go up because that's where the z is. So let's pretend that that wasn't there because yours doesn't have it, okay? And let's first look at the coordinate points and then we'll work our way backwards. So if I start at 0 here, okay, and I want to go 2 towards the x, it's a positive 2. So I go towards the x. So that brings me forward 2 spaces. Then I want to go 3 for the y, but I want to go negative. The y is over here. So I want to go away from the right, which means I'm going to move 1, 2, 3 to the left, sort of diagonal left. And then the last part of that is positive 3, and the z's at the top. So I want to move up 3 spaces, 1, 2, 3. Now this is not in line with this 3 because this is a slanted graph. So it's a total approximation. It doesn't have to be perfect, okay? But it is not directly in line with that 3 on the on the z-axis, because this is like flipped forward. If it was totally flat, you wouldn't see the axes, okay? So that's the coordinate point that you would use, 2, negative 3, 3. Yeah. Oh, thank you. So let's just say I wanted to name this coordinate point over here, okay, the one on the right. I would move back 2, so my x is going to be negative 2. I would move 1, oh, you can't see that, 1, 2, 3, 4, 5, 6 to the right. That's what this coordinate point is. And then, good, 1, 2-ish up. Okay, the up is the hardest part to see because we don't know how big of a slant that is.
Everything's just going to be ish, right?
Unless it has the lines, like this is exactly 6, right?
Okay.
So that we can see this is exactly 2.
Up.
It's the up that's going to be the hard part. All right, plot each point. And again, what I would ask you to do is give yourself those little scoops to count the up so that I see how far you intended to go. And there's no lines this time. So try to move parallel to your axes to get to those points. Notice the x is at the front, the y is at the side, and the z is at the top. All right, so for the c, the negative 1 is your x. So if I start at the middle, I'm going to move back 1. I did move.
Which way is forward and backwards for the x?
The x, so towards the letter is positive.
Oh, okay. So.
And then away from the letter would be negative. So in this case, it's forward, right?
Yeah.
So negative is back 1. The y is 3, so I move 1, 2, 3 to the right. And the z is 4. I'm going to go 1, 2, 3, 4. Again, it doesn't have to be exact. You want an approximation, and then I'm just going to label that point as C. Now D, 1 forward, 3 to the right, 1, 2, 3, up 2. And E, 2 forward, 1 left, 1, 2, 3, 4 up. That's your bell.
See how this
Yeah.
would really be bad drawing lines.
This is not fun. Yeah, I don't even know that I'll make you plot points on your test, to be honest. What's left over is what will probably be on your test.
But like drawing this is gonna.
Yeah,
Yeah.
yeah. Wait, who am I losing tomorrow for A push? I know overall how many I'm losing. You guys? 1, 2. Oliver, Marcus, Michelle, Sophie. Okay. Want to get an idea of what it would look like. So if I wanted to plot a point, I could come in here and I could say change my x to -1, and that red dot just went backwards on that x-axis. And then my y being, what was it, 3 or 4? 3. It's moving to the right 3 places. And then my z up 4 places. It's literally traveling up. So you can kind of tilt this in so that if you could see it as a flat surface, it would be floating above the surface. Does that make sense? Because you're going 4 up. So this is a good tool to kind of help you visualize those coordinate points. if that kind of question is on your test, it may be like, here's the graph, like almost like the first question. Here's the graph, give me the coordinates of A, or give me the coordinates of B, or vice versa. Which one matches these coordinates? So there's a little bit less left to your imagination because that's the hard part. It would be something like that. So I'm going to quick go over the next part because we're about to leave. We will work out the examples tomorrow in class for everybody that's here. But for the kids who are taking APUSH, if you can understand, which it takes 5 seconds to understand this because you already know it, that we are going to find the distance and the midpoint using a third coordinate point. You already know how to do this with 2 coordinate points. We literally are just adding the z's in. So if I want to find the distance between 2 3-dimensional points, then I do the distance formula with the x and the y, but I also add in the z here. So the distance formula used in space is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So same exact thing that you're used to with the distance, but we add on the z's. This will be a square root. It will be a whole number if you can square root it. It will be a simplified square root if you can simplify it, okay? But you'll keep this exact. You won't estimate this. And then the midpoint is the midpoint between these. So it's the same formula as the midpoint we're used to, except we add in a z. Add the 2 x's, divide by 2. Add the 2 y's, divide by 2. Add the 2 z's, divide by 2. Easy stuff, right? Again, I will work out these examples tomorrow. So the folks that are in class tomorrow, because I know I lose some of you to the exam, the folks that are in class tomorrow will work through these examples. And the last thing is the equation of a sphere. So instead of a circle, because we're in space, we have a 3-dimensional circle, which is a sphere. So our standard form of a circle is our x minus, which is on the next slide, x minus h squared plus y minus k squared, and it comes from the distance formula between the radius and a coordinate point. Now it's the same idea except it's a sphere. So the standard equation of a sphere is x minus h squared plus y minus k squared plus z minus j. Do not ask me why it goes in that order. That's not alphabetical. I don't understand it, but it's going to skip a couple letters and go right. We don't have I. Okay, I guess we're trying not to confuse it between a complex number. Equals r squared. So the center is your h, k, j, and your radius is r. So we're just adding on another coordinate. And then the last thing we're going to do here is find the equation. Again, I'll work through these tomorrow. I just want to do a quick review. And just when you thought you were done with complete the square, we have to put this in standard form. So you would group it. Now you're going to complete the square not once, not twice, but 3 times. Okay, I will go easy on you for these. If you look, they are all even, so you're not dealing with fractions usually. I mean, you can, but not a lot. And then you'll put this in standard form. And again, we'll work this example through tomorrow. So if you are not here tomorrow because of APUSH, good luck. Okay, and you can work on the homework if you choose to. If you need the extra day, I understand it's a lot of pressure for tomorrow. That's okay too. If you are here tomorrow, we will work through these examples and you'll probably get time to start the assignment. Danny? Sure.